quite possibly one of the coolest things. There's lots of different ways to make an electric motor. We're going to talk about simple, basic electric motors because they're pretty easy to describe. However, if you know anything about technology, as technology advances, so the electric motor has improved dramatically over the years. We will make a single pole brushed motor. That's what we're going to make. If you want to look up what kind of motor we're making, that's what we're going to make. But today's motors have advanced beyond that. Most motors are no longer brushed motors. They're called brushless motors, which means they have no parts that can easily wear out. The electric motor, the part that spins, is isolated from where it's getting its electricity, where it's getting its potential difference from. And this allows it to work for a much longer period of time. We're not going to go and make that too huge of an advanced motor, but also most motors are multi-pole motors. And I've come to grips with the idea that you guys don't necessarily know very much about the way things work. We've had this conversation a couple times. Like an automobile, it was clear most people don't understand how an automobile works, how it converts the heat energy into physical energy, into kinetic energy. Is there anybody here who's familiar with the process of the internal combustion engine? Okay, so we have an idea, or some of you do. Is anybody familiar with what the Carnot cycle is as it pertains to an electric motor? Okay, so it's part of the result of applying the second law of thermodynamics to a heat engine, which is what a internal combustion motor is. I want to start by talking about how you build a simple motor. We have two things to bring to bear here. The first is that we are aware that the magnetic force on a current carrying wire is equal to IL cross B. Talked about that yesterday. Now, we have to add a few things to this because we're going to be talking about mechanical energy. So it would probably be appropriate that you remember some mechanics. And the first is torque. Does anybody remember how you calculate torque? Go ahead, Vicki.
R cross F.
That's right, R cross F. Now in R cross F, and both of these of course are vectors, R represents
The distance of the work from the pivot point to the...
That's right. That's exactly right. It represents the distance from the pivot point to where the force is applied. And then we call that the torque arm. And then F would be the application of force. Good enough? So I want you to consider a region of space where we have a magnetic field. Okay? And I place a single wire in that space. With a current passing in this direction. This is just our starting point because every day, if you've noticed, I put something on the board to require you to use the right-hand rule. Today is no different. So would you take a moment and let me know the direction of the force on this wire? Everybody always says it's so delicate. We know that the force on a current carrying wire is going to be based on this product, but also the direction is yielded from the right-hand rule. If we're careful, we could probably design something that could apply a torque to a system. Now, we'll have to have an object that can receive a torque. So let's consider a different situation. One where we can have an object that can receive a torque. So I'm going to take my wire and I'm going to bend it into something that can receive a torque. And to do so, I need to make it so it has a pivot point or a pivot somewhere in the object. So I'm going to say bend it into a square. So I've taken a just piece of wire and bent it into a square. Let's go ahead and make some decisions about this. Let's say that this isn't very square shaped. I would like it to be more square shaped. So, let's see, can I make something more square shaped? Nope. That looks more square shaped. There. Does that look nice and square shaped? Will you guys accept that as a square? Thanks, you're swell. So I'm going to say that the side length is length S, and this is also length S. And I'm going to try and bring these pieces as close together as possible, but I don't want them touching. And you'll understand why in a moment. There, so very close together, but not touching. There we go. Because I want to be able to connect these two wires to a potential difference to generate a current. Does that make sense? So external to this, I'll make this the positive side, this the negative side. That will generate a current that will go like this through the wire. All right, so I've made a current loop. You're going to hear the word current loop a lot. So this is our current loop. Now, I want to place this in a region of space that has a magnetic field. And I'm going to make that magnetic field go this way. And I'm going to try and surround the whole system with as much of a magnetic field as possible, but all pointing this way. Okay? So this is our magnetic field. Now, let's use a right-hand rule and determine the force on the current carrying wire. I think there's 3 places that we have to determine that force, say along this length, and along this length. Follow me? So let's do the first one. So, right-hand rule, current, magnetic field, I see a force that is out of the page, right? All right, so force this way. And can we kind of agree that very little or no magnetic field is going to act here because it doesn't define a plane? Our angle is 180 degrees. So along here, F equals 0. And this way, let's see, magnetic field, I'm sorry, current, magnetic field, into the board. Is that all good? Now there's a uniform current in the wire, so I know that based on what I've just drawn, if I was careful to select it, I could say that this is going to be equal to ILB because the angle is 90 degrees. And instead of L, I'm going to use S because that represents the side length of my square. And it's possible I could write I in terms of, say, the applied potential difference and the resistance of the loop. I want to keep that in the back of my mind too. Everybody good? So there's a potential difference here of V, and we'll say the loop has some internal resistance R. Generally, we try to keep the resistance of the loop relatively low, as with its mass, if we wanted to get to turn easily. Now, you guys can see from just this description that we're going to have a torque applied to this loop because I'm lifting up on this portion of the loop while pushing down on this portion of the loop. Does that make sense? Well, right now, you should be able to compute the size of that torque. We have enough information to do so, because I think you could also agree that this represents the center of the square, And if no other forces act on this loop, this would be the length of the torque arm on the square. Fair enough? All righty. So let's work out some details about the torque. Based on the way it's structured right now, the force is perpendicular to the torque arm because this length is our torque arm. That good? Everybody following with me? So we'll have R times FB times a sine of 90 degrees. With a little substitution, I can write R as S over 2, right? Half of the side length. F will be ISB. And if I'm dealing with net torque, well, there are two of them. Equal torque on both sides, and both torques in the same direction. In fact, we could talk about the direction of the torque because you know the right-hand rule. Direction of torque from the right-hand rule. You go in order. R cross F means the torque is out of the board and is going to cause this thing to twirl like that. You follow me? This torque, I bet on this side, will be into the board. R cross F, right? Because this is my torque arm length, and into the board is my force. It's going to cause a similar torque. Now, this system will cause the system to rotate and will give us a rotational motion, but it's not going to last very long, is it? Do you guys see why it won't last very long? Because this will be the start, and this will be the starting torque. But when I look at this, I'll get my, 2's will cancel. I'll get S squared in there, so I'll get I S squared B. Right? This isn't accidental. This is the area of the loop. It can be shown that regardless of the shape, the torque will be the same, even if it's not square. So if I change this and say use a circular loop, that area, although different than the square, would still determine the size of the torque. I'm not going to prove that to you, but it is something that can be proven. Does everybody understand? So if I was to replace this with a loop that were circular, which is actually what we're going to do in lab, so it's reasonable to think about it that way. A circular loop that would fit in this same space, it would have less torque because it has less area, but it would still be based on its area. And like I said, proving it to you is not easy to do, so I don't want to have to. It just has to do with the fact that the torque is more or less similar, but the torque arm length is different along all of those different passages, right? The torque arm length here would be different than the torque arm length here. So you'd have to sum that using an integral. It's just not particularly interesting, but it would show that the area still works. So that being said, I want you to consider the problem with this. This actually represents the maximum torque. Because here's the problem with our motor. Take this and just put it aside for a little bit and consider that the only two wires that actually matter is this wire and this wire. Is that okay? You guys understand why those are the only two wires that matter? We good to move on for just a second? All right. So I'm going to draw this from the side. This represents the wire on the left and has a current that is going into the board. So I'll move that dot out of the way and just say that this is my wire with a current going into the board. This is my wire with a current coming out of the board. That matches up with what's up there. You guys agree? I'm looking at it as if I'm looking this way. That okay? So I'm changing my perspective. The magnetic field currently is this direction. Now, again, right-hand rule. Current magnetic field, force up. Current magnetic field, force down. So we got force up this way, force down this way. And they are connected by a wire. Right, because it's a square. Well, right now, this represents the angle between the applied force and the torque arm. And it's 90 degrees right now. But the moment we actually set this into motion, that's not going to stay that way, is it? Let me just put that connecting wire back in. As this thing turns, that angle changes, right? But even right now, do you realize that the force is still straight up on the left side of the wire and straight down on the right side of the wire? You guys all see that, right? So what's really going to happen is this object is going to move to here. By the time it gets here, it has momentum. So it could pass this point. But if it passes this point, what direction is the force on the top wire?
Up.
Still up, right? And what direction is the force in the bottom wire? So our motor will flip to here, and then we'll do this. And if there's any air resistance, it'll just stop like right there. Not a very interesting motor. So you have choice about how you can build your motor. A single pole motor will be set up so that when it makes it to right about there, the current switches off. If the current switches off, there's no longer a force acting on that portion of the motor, correct? So our system can continue to move due to its inertia. But then when it gets back to, continue to move according to its inertia, when it gets back to say right about here, boy, I would like it to turn back on, wouldn't I? Because if I can get it to turn on right there, I'll suddenly have a force this way and a force this way to cause the next flip. Does that make sense? This is a single pole motor that it turns on when it's advantageous to cause a flip, and it turns off before it gets to a point where it's going to be locked. Now, single pole motors are okay, but you probably realize that if you could, it might be easier or better that when you make it to here, instead of having the current turn off, have the current flip directions. Because if I could have the current flip directions, the moment I make it to here, this becomes the opposite side and this becomes the opposite side, and suddenly I can flip now. This is a two-pole motor. There's a couple of ways to build multi-pole motors. One of them is to have two coils. One that's lined up when you have it one way, and one that turns on when you have it lined up the other way. The other one is to have different brushes on the system. The brush is the part that connects the motor to the potential difference. That's a wire that just scrapes around the outside of a semicircular loop, so that the brushes just kind of touch the outside of it, with one side of it connected to one part of the battery and one side connected to the other part of the battery. A simple motor like this does develop torque. We're going to do the single pole motor because it's easier for us to build. If you are interested in building a dual pole motor, I can show you how it's done. Most of the time, motors are built with 3 poles or an odd number of poles, meaning they don't have just one set of loops. They have a loop maybe oriented in a different fashion, like this way, and then another set of loops, say, oriented this way, That way, there's always one loop that is near maximum torque. If you have multiple loops like this, you're always producing maximum torque. Our motor, which only has one loop, produces maximum torque only once when it's oriented this way in the field. Every other time, it's actually developing less torque. Are we all good so far? Let's talk about that torque for just a minute. You know, one of the easiest ways to have more torque? Have more loops. If N represents the number of loops, you get twice as much torque by just having 2 loops. You understand how easy that is then to create more torque. The more you wrap your wire, the more torque you get. It's an excellent benefit, but there's a downside. The more you wrap your wire, the more resistance your wire presents to the battery. So for each loop, you increase the resistance and you reduce the torque, which probably tells you that there's a couple of things you can do to maximize the torque of your motor. 1, use more current, increase the voltage. 2, use a wire that has low resistance. That's obvious, but yeah, low resistance. Next, increase the area presented to the magnetic field. Most motors have lots of loops, hundreds, thousands of loops, because it produces so much more torque compared to how much resistance you add. Each loop does double the resistance, but the resistance is already very low. Most of the resistance is in other portions of the circuit. So resistance generally isn't the problem. Generally, the problem has to be the brushes and heat that's developed in the motor, because you get so much torque on a simple motor like this. So we're going to build simple motors. And I do want to point out there is another part to this that we're not going to get into too much, but the amount of acceleration you get will be directly dependent on what the moment of inertia of your motor is. Now, if you remember all that from last year, you'll understand that we have a small ring that is flipping about its center. The moment of inertia isn't very high as long as you keep the torque arm a little bit small. So although you get an increase in torque by having more area, sometimes it's not too advantageous because it increases the moment of inertia. It's a balancing act. So we'll make simple motors using that principle, but you should be able to calculate the maximum torque of the motor. I do want to say that if we didn't want the maximum torque of the motor, we could edit our function. Edit our function by just saying the torque is based on the angle the motor makes with the magnetic field. That works too. So if you just add this angle in there, it tells you that you get a torque that is based on a sine curve. And I don't think that's a surprise. Has to be moving in order to create a magnetic field. Now, this is, I don't write this lightly, this is not an obvious equation, the way it's set up. And in order to determine the magnetic field, we use an equation called the Biot-Savart law. And I'll be honest, I don't know very much about either of these scientists, or if it's just one scientist with a hyphenated name. We won't use it very much. But as you can probably imagine, there's going to be a law that is similar to Coulomb's law. And then there's going to be a law that's similar to Gauss's law. There's one of each. So we're going to see just one of them today, but we'll fill out this chart because there is a law here that has the same kind of symmetrical relationship to the magnetic field as Gauss's law has to the electric field. So today we're going to talk about the Biot-Savart law, but there are 2 expressions of the Biot-Savart law. The first expression is the magnetic field from a single moving point charge. And so we'll say it's B, because we're talking about the fact that the magnetic field is represented by a capital B. It does have direction, and prepare yourself, mu naught over 4 pi times Q V cross R hat over R squared. This is the Biot-Savart law as it pertains to a point charge moving through space. Now, It's an unlikely scenario, and you're probably very unlikely to have to use this version of Biot-Savart, but it's where we start. There's another version of Biot-Savart that works for a current carrying wire, and it's not much different than what you would probably expect, because you can probably see some symmetry here that's reflected here with the QV and the cross product. So we're probably going to see something like that here for Biot-Savart for a current carrying wire, but it only tells us a portion of the magnetic field. It's something that we would have to sum up for the entire contribution from a long current carrying wire. And it looks similar, has a similar structure. But instead of Q times V, we'll have I times ds, where S represents a small amount of length, and that includes the direction of that length. Still cross R hat, all divided by R squared. So these are the two versions of the Biot-Savart law, and they can tell you the size of the magnetic field of either a moving point charge or a current. Now, there are clearly features that are shared here, and this shouldn't surprise you. We had a similar feature here. So we had epsilon naught in our discussion of the electric field. And we didn't start with that. We started with Coulomb's constant, but now we've come to understand that Coulomb's constant is based on the permittivity constant. So if I was just to put these up here nice and high so you can see them, you'll remember that the permittivity constant was the manner in which an electric field can be established in free space. We called it the permittivity constant. And this is got a similar side over here, but we call this the permeability constant. It's the exact same thing as the permittivity constant, except that it's about how a magnetic field can be established in free space. The permeability constant. Interesting fact about these two, they can be measured independently. You can measure one by just measuring electric fields and forces on charged particles, something that can be done quite straightforward in the laboratory. Permittivity can be measured the same way by measuring magnetic fields and the force on charged particles, something that can also be measured directly in a laboratory. Interesting thing about that is together, these two predict the speed of light. And it's not clear from where you're standing now how to do that, but by the end of the year, we're going to be able to develop a wave equation that would predict that light is an electromagnetic wave based on and drawn from two very separate theories that were developed without any thought to light. And it's interesting that the fabric of space can predict how fast light can travel through it. It's kind of an interesting diatribe, but we'll need to take some time to get there. And it'll be a bit of an aside the day we get there when we finally have a chance to talk to you about Maxwell's equations. So I want to talk just real briefly about the first law, but then talk to you really about how we use the current version of that law. All right? Because there's a lot of pieces there. So let's start by having a point in space where we have a charge with a velocity in this direction. Because there's something kind of strange about the magnetic field. So let's say I have let's make this positive for the time being, a positively charged particle traveling with a roughly horizontal velocity to the right. The Biot-Savart law says that a magnetic field is produced based on this construct. Okay? Now, let's pick a place in space to describe the magnetic field. And I put a X there, but I really don't want to put an X there because I don't know whether the magnetic field's going into the board or out of the board at that spot. So I'm just going to put kind of this is the location in space that we're going to look at right over here. This is kind of an odd cross product. And for those of you who may not know or don't remember, what does R hat represent? It's a unit vector. What else? There's something more. It can be the unit vector in the direction of the torque arm. The R part here represents direction. And the problem we have with this function is that we need a direction for our magnetic field at the end of the day. And to determine direction, we use a cross product. The problem is that the magnetic field, like the electric field, decays as you get further away from the charged particle. The farther away I am, R, that would be this distance from here to here. That's R. It determines how far away from the particle you are, but that also tells you how strong the magnetic field is. It tapers, just like the electric field, as an inverse square. So the further away you are, you double your distance, you have 1/4 of the detectable magnetic field. But we also use R to determine the direction of the magnetic field. In order to do that, we don't want to affect the value of the magnetic field, which is why we multiply by 1. So R hat is a unit vector. It has a value of 1. But it carries with it the direction information. The direction between our location in space, say point P, and where our particle is in space. Now, the same things that we've done already apply in the case of this particle from when we talked about electric fields. Meaning, if we get away from the directional aspect of our answer and just care about the fact that that's R and we have Q and V, the size of that magnetic field is going to be mu naught over 4 pi QV over R squared. If all I care about is the magnitude, ignore the cross product information for the time being and realize that that's got to be the case. However, it is scaled by the angle between the velocity and the R hat vector, with maximum magnetic field being related to when they are perpendicular to each other. So I chose this location, but the particle's moving to the right. I will do better when the particle has made it here. Because not only will R have gone down, but it will improve the value placed in the sign because I will approach a 90-degree angle. Does that make sense? So the value of the magnetic field is not only tapered by the distance away, but also the angle that I face relative to the motion of the particle. Now, let's talk about the right-hand rule aspect of this, because that part's going to get harder, okay? How do we categorize the direction of R hat? Do you remember? And what I mean by that is, if we look at this picture, and let me just zoom in on the picture, is R hat relative to the particle that's moving, therefore it would be in this direction, or is R hat relative to the point in space where we're sitting and watching? Do you remember? Because it's going to make a difference, isn't it? Any chance that it's in your notes and you could look it up? Because it would be important. It was a long time ago. We're talking like the first month of school. That's how long ago we're talking about. All right, it's going to take you too long, and we don't have that kind of time, right? Yeah. What's that? All right. Well, I need to conclude this. It's relative to the particle as it's moving. So here's what I want you to understand. V cross R. Okay? It's V cross R, where R is relative to the particle. The reason this is important is this means that the magnetic field is out of the board at this location. You understand? So if the particle is going this way, it creates a magnetic field that way above the particle. If you extrapolate that all around the particle, you find that the magnetic field presents a circular field around the particle. In fact, ahead of the particle, you get small circles because the magnetic field isn't very strong. And the circles grow as the particle passes your position and then fade again away behind the particle. But they pass in a circle around the particle. In fact, it's easier to use the curl rule to determine the direction of the magnetic field. If you point your thumb in the direction of the velocity, your fingers curl in the direction of the magnetic field. So you might find it easier not to do this one, but to do this one. Now, this is important. Magnetic fields have no point of origin and no point of termination. Electric fields originated at positive charges and ended at negative charges. Magnetic fields are circular and complete and have no point of origin and no point of termination. There are no monopoles in the magnetic sense. All magnetic fields are circular, all of them, which means everything you've been taught about the north pole and south pole of a magnet is wrong. They don't really have poles in the sense that you think they do. If you break a magnet, you create a new north and south pole. Yeah?
So by the curl, would the arrows in reverse?
Well, it's coming out of the board here on that side and into the board there. But I can't draw it in 3D very well. So maybe I have my arrows. I see that this part is on the outside of the board. It should be going downward on this side of the board and then upwards on part of the board I can't reach because I'm in the other room. Does that make sense? So I'm trying to make my arrows look like that. This part's on our side of the room and this part is on the other side of the room. But I guess that's not great because I'm in a hurry and I'm down to 18 minutes, right? So I'll do a better job when I draw my picture later. Is that better? Like getting rid of that one little thing? I don't know. I'll do a better 3D picture job later.